Hello and welcome to the Pharmacy Informatics Professor 2020 with your host, Dr. Armin Simonian. Today, we are honored to have a return visit from one of the pharmacy informatics pioneers, Dr. Dennis Tribble. And Dennis, on your first visit, you talked about your career path, and you mentioned that you had created and built an IV preparation robot. And I promised my viewers at that time that I would have you come back and talk specifically about that very innovative and fantastic project that you did with building that robot. So as a certified pharmacy computer nerd, I'm very super excited to hear your story. And I'll hand the microphone over to you, and you can tell us how you came about creating and building and selling a IV preparation robot.
Thank you, Dr. Simonian. And just to check to be sure that the presentation's up on the screen and all that kind of stuff.
Looks good. Yep.
Okay, great. So I actually enjoy talking about this particular subject because this is something that's really near and dear to my heart. I was actually given the opportunity to start work with a startup company that made something called IntelliFill IV that was a robotic device. It was the first robotic device to completely automate a sterile compounding process. Now, specifically, this made 10 ml syringes, so it probably wasn't as useful as more modern day robots tend to be, but we learned a lot in the process. This is no longer available on the market, which makes it fun because I can talk about it without worrying about anything. Right. But as you can see, it was about the size of a refrigerator. It had a pretty crowded set of automation. So one of the things we want you to learn is that it doesn't have to look like R2-D2 or C-3PO to be a robot. It just has to be able to do things that it needs to get done. At its fastest speeds, weighing every syringe, this device could actually prepare upwards of 400 syringes an hour. And if you were willing to weigh every 10th one, it could get up to 600 syringes an hour. So it was pretty fast. So what kind of things do you need to think about with this robot? Well, the first thing you think about is control systems. How does the robot do all the right things in all the right sequences at all the right times and know when it's doing something wrong? So there have to be some central control systems that know all of the pieces, know how they're supposed to move and how they're supposed to go. If the robot software is designed right, it can produce a wealth of information about how it works. And it turns out, especially since this is a medical device, that documentation turns out to be really, really important in terms of being able to demonstrate to the FDA that the device actually works properly and has a history of working properly, as well as providing great information back to the people who make it about what's working and what's not. Because it has to maintain an aseptic environment, you have to be able to clean it, which means you can't just shove a whole bunch of stuff in there and leave it alone and never touch it. So people have to be able to clean it without hurting themselves and without hurting the robot. And it has to have safety systems both to prevent it from starting up when someone's serving it, as well as to force it to stop if it looks like it's going to hurt itself or a human. And then sensors to detect failures and systems to continuously monitor its accuracy and its reliability. One of the big issues you really worry about in the design of a robot was how long can this operate independently without human intervention? This is one of the things that with this particular device, we never really got to be ideal, primarily because its syringe supply would become exhausted in about 15 minutes. So somebody had to come back and touch it roughly every 15 minutes. But if you could do something else while it was working, you had 15 minutes to go do something else. You didn't have to stand there at the robot all day. Speed compared to a human is always an interesting question. The technicians who often use that would use this or would worry about being replaced really don't want to believe it's useful unless it's faster than they are. But it turns out that because they don't take breaks and they can work unattended for some periods of time, they don't really have to be as fast as a human being as long as in net they get the work done. Having said that, if you're in the business of selling robots, you better make them fast enough that people are really amazed by them. And then the big issue that has often plagued robots in general is reliability. That is, how often do components fail? What kind of preventive maintenance is required to keep them up and running? And how reliably can you walk away from them for that 15 minutes without having to come back because something decided to stop? You're also worried about how information gets into and out of the robot. So what kind of controls, what kind of connections does it need to a hospital network, for example? What kind of interfaces are you going to use? I will tell you that in this particular case, we started this device with what's called a print stream interface. We literally took the labels that were printed for IV making anyway by the HIS, and we read them automatically, figured out if we could use that, could make them, and if we did, we would make them, and if we didn't, we would send them on to the printer. This did use disposables, and most IV robots will, because it turns out that even though the robot is exempt from certain FDA requirements, the fluid path inside the robot is not. So it's much better to have the disposables being built by someone who already makes IV tubing and other things than it is to try and make it on your own. Printing turns out to be a really interesting problem. So imagine that you have to somehow print and apply and verify, which we did with a barcode scanner, a label to every syringe as it goes by at the rate of 400 to 600 syringes an hour. It gets to be a pretty good trick. It can be done. Here's a hint. You can't use a standard Windows print server routine on that. It's too slow and too unreliable. You really have to treat the printer as a serial device that you're controlling from within the robot. And then, of course, when items fail, how do you recover? What kind of information are you presenting to the user that allows them to recover from the error and keep on working? How do you detect when something has gone wrong? And we used a lot of things to do that. We used sensors to make sure the components were moving in all places. We had an airflow sensor to be sure that the HEPA filter was working. We had air and line sensors to detect if we were out of fluid and those kinds of things. We had light curtains that would detect when something passed through them, so we could see that something had dropped when it should have, or hadn't dropped when it should have, and those kinds of things. So you build all those in. Typically with a robot, you build in more than you need and take out the pieces that turn out not to be valuable later. Software design is very important because you're managing a whole bunch of components operating in real time. I could do a whole talk on that, so I won't go too much further. Your mechanical design is important. You saw how crowded that was in there. That means that you have to design the entire set of apparatus so that no two things will collide with each other, moving through three-dimensional space. You really have to have very extensive and risk stratified software development. So the first thing you do is identify the pieces of software in your system that are so critical that you have to test the whole thing if you touch them at all. And those mission critical pieces of software you have to build with extreme care, package them up on the shelf, and then never touch them unless you absolutely have to. And that actually makes it easier to get through things. Vision systems turn out to be fairly important because sometimes it's the only way you can tell when something is not quite working right. One of the things that really helped us was we actually taught this. It had its own modem involved. It would actually, this is back in the days when that used modems to dial home. We would actually have the device phone home every night and tell us everything it did all day. No EPHI and all that, but it was all the statistics about what it had made. And then again, there was some hardware design that actually was pretty challenging. Robots, by and large, are what we call erector set technology. You don't typically invent new pieces for them. You find standard components like grippers and sliders and servo motors and arms and conveyor belts and automated syringe pushers and those kinds of things, all of which are commercially available. And you assemble them into what you're going to make. So for example, if you're looking here now inside this particular robot, we used a stepper motor. Well, let me just start back. We had a gripper that could pick up a vial, take it to be to get fluid put in it. And then when it got done, it was attached to a slider that would move it over to the reconstitution unit. So it would actually turn it over and drop it into this circular piece, which would close. And it had sensors that knew when it was closed. And that was driven by a stepper motor. Now, a stepper motor is a motor that knows where it is within 1 degree of arc. So if you have 360 degrees of a rotation, it knew where it was within 1 degree. And you can tell it to go in either direction so many degrees at a given speed. So it could shake fast or slow. It could move all the way. In fact, one of the things it would do before it started shaking was to turn it upside down so that it would get everything wet and then start shaking. But we had actually started with a standard agitator for reconstitution. It took 20 minutes to reconstitute a cefazolin 10-gram vial. This would reconstitute a cefazolin 10-gram vial in a little under 45 seconds. So it was considerably better. We did talk about the fact that you have regulatory concerns. So the fact that it's regulated as a Class 2 medical device by the FDA means that there are constraints on how you manage both the software and the hardware, and what you can claim and what you cannot claim about the device. So it adds a great deal of rigor to the development and servicing process. You do have to worry about occupational and safety hazards, not just about how the robot works itself and making sure it won't hurt somebody in the process, but where can you put it, right? If you're in California on an earthquake zone, you probably can't put it much above the first floor, because the floors probably aren't designed to hold that weight, especially in the presence of an earthquake. And even if you're on the first floor, you have OSHPD requirements where you have to tie it down so it won't fall over it if we get a 7-point Richter, right? In many cases, individual state boards of pharmacy have regulations about adopting this technology, especially if they're unfamiliar with it. And so they may have requirements for review and for certification and for demonstration of efficacy and all those kinds of things that you have to worry about. Since you are labeling doses, especially if you're using it for patient-specific preparation, by definition, that means that it has access to electronic protected health information, EPHI, which means you have to have the protections in place to be sure that it could not be inappropriately disclosed. And because you're making compounded sterile products, you have to fit into USP 797. So there's a lot of things on a regulatory standpoint that you have to think about as well that we had to build into the robot. But the reality was that it did get out on the market. By the time it was done, it had made several million doses, and by and large had been pretty effective. So I'm very proud of it. I'm very happy we had the opportunity to do it. And I think a lot of the learnings that we did that actually went into or moved into the development of some of the first IV workflow products. Because if you could make a robot do it, you could help a human do it. And that's my story.
All right. Thank you, Dr. Tribble. Excellent. And wow, you're a very creative individual, and you came up with something unique that has now become basically a new standard in pharmacy informatics. So thank you for all your contributions to this specialty area of practice. Excellent. I found it very interesting to take a peek behind the curtain that you gave us to see all the different considerations that you have to have in building a robot. It's not easy, but you did it. So great job. And to my viewers, to my viewers, if you found this interesting, please like the video and subscribe to my channel, and I'll thank you for that. And in the meantime, stay safe, stay healthy, look after the health of others, and I hope to see you next time. Take care.